Hello and a very warm welcome to the world of material sensing. My name is Robert Langer, and in this video we would like to shine some light onto the Senorics material sensing technology. We would like to learn more about why it's special, how it actually works, what kind of advantages you get with it, and what you can do with it. And here with me to actually have a closer look is our CTO, Dr. Robert Frückner. Hi.
Hi, Robert.
Hi. So let's start with a very generic question again. What is so special about Senorics technology? How is it different from what we have or what we see on the market?
So what we see on the market is usually conventional spectroscopy solutions. It's composed of a dispersive element, a grating or a prism, something like that. And you need lots of space and you need to put it into a lab in order to have good results out of that. And we at Senorics, we developed sensors looking like that. We have different spectral region coverage here. So we have individual pixels which are responsible for individual spectral regions. And we have no moving elements. We have no additional optics required to take a spectra. And therefore, this is regarded as a low-cost sensor. It is very, very fast, quick, because there's no moving element, and these are standard PIN diodes, so we can measure really, really quick. Yes.
Wow. And one thing that is also worth mentioning is that this is not made of all the detector materials that we see on the market, but this is a very special combination. This is made of organic semiconductors. Can you dig a little deeper there?
So right, organic semiconductors are known from display technology. For example, in many smartphone displays are composed of organic materials, and they are advantages compared to other display technologies. But when it comes to sensing, it's very new to use organic materials. And in our organics world, we can combine the power of silicon and indium gallium arsenide, so we can combine the spectral regions. We can cover the entire spectral region of silicon and of indium gallium arsenide from 400 to about 2 micron, and yeah, at low cost.
Okay, so and then there's one thing that a lot of people ask me if they hear organic semiconductors. There's this confusion that actually a lot of people think that you can eat it or you can compose it. So, but this is not true. You can actually, or you should actually not eat our sensors because you then cannot do material sensing anymore. But maybe you can again shine some light on what does organic actually mean in organic semiconductors, and how is it different from anorganic semiconductors?
So organics, it's not living or something like that. You can compose it. It's non-toxic in comparison to, for example, indium gallium arsenide. It has a molecular basic structure and it's organic molecules basically. So carbohydrates and things like that. Plastics. That's a good translation for organic material. And yeah, it's non-toxic and you can easily use it for many applications.
Mm-hmm. Okay, so basically organic being a more chemistry-related word here or meaning here, so that it's most of the time it's carbon-based materials that we use, right? Okay, so that we have this confusion out of the way. Let's dig a little bit deeper in our technology. You mentioned that we have no dispersive element, for example. That's a very traditional, it's very typical for traditional spectrometers. You mentioned that we have individual wavelength coverage here. How does that work? How do we utilize these organic materials to absorb the light? Can you dig a little bit deeper in the sensor principle?
Yeah. So usually in conventional technology, you have a broadband detector, and you need some conventional dispersive element, which is disentangling the white light into the individual spectral regions, and then the detector sees only monochromatic light. In our case, we don't have a broadband detector, but we have a narrowband detector. We can tune the spectral parameters, the spectral sensitivity over the complete spectral range, and we can really tailor our spectral response to the application we want to target.
Mm-hmm. So basically, when classic spectrometers use silicon or indium gallium arsenide, they cover all wavelengths at once and they need to split it up, while we have actually individual pixels that can only detect one wavelength, and we can even tailor this to the wavelengths of
Yeah.
the application.
Yeah, exactly. Yeah. And we don't need the huge space, which is a standard spectrometer needs to disperse the light. You need distance between the optical components to the detector, and we have all of that is on this substrate, and the detector itself is less than 1 micron thick. Mm-hmm. The thing you see here and you feel here is only the glass substrate where it is put on.
Mm-hmm. Okay, so let's dig a little bit deeper into the advantages. You already named them all, but let's go through them a little bit more in details. And let's start with the spectral coverage. You already mentioned that we can cover both the visible as well as the NIR spectral range. So we can cover everything from 400 nanometers on the low end, on the blue end, if you will, all the way up to currently around 1800 nanometers. How do we do this? How do we actually make sure that we hit these wavelengths, these individual wavelengths?
So we have in production of our sensors, we can tune several parameters which make sure that we address the right spectral region. We can always go for the right spectral region. We can tune the spectral width of each band. It needs to be narrower in the visible spectral region because there you have electronic transitions from materials. So the color is representative for that, and we can make it broader in the NIR, which is good enough to have material sensing in this spectral region.
Mm-hmm. Okay, so we're basically using different material combinations to account for different wavelengths, right?
We don't necessarily need different wavelength, different material combinations. So we found in our patented technology good material combinations which can cover basically the entire range.
Mm-hmm. Getting back to the advantages, second advantage that you mentioned is that we do not need a conventional dispersive element. How does that work? How can we actually do spectroscopy without a conventional dispersive element?
So a conventional dispersive element as a gratin or a prism needs to be placed at a certain distance from your broadband detector. So this is a clear disadvantage, and we don't have one element which is dispersing the light, but we have different filter technologies. So each pixel is equipped with a certain filtering component which sorts out the right spectral regions and translates it into an electrical signal. So we have a spectral resolved pixels in plane, so we don't need to place to have another dispersive element in place.
So basically, each of our pixel is wavelength selective. So it's just it just reacts to a certain wavelength, to light of a certain wavelength, and it is not interested and not actually even able to detect wavelengths of other wavelengths, right?
That's the basic condition, yeah.
Yeah. Okay. Moving on with the advantages. Next advantage that you mentioned is that we are low cost. Now that's a very fuzzy term, low cost. How do we achieve low cost, and what do you actually mean by low cost? To how low can we actually get with that technology?
That's a good question. So this is organic electronics. I mentioned the thickness of the device. It's less than a micron. For example, to produce the sensor, you need a glass substrate. Then you need organic substances. And for example, with 1 gram of the organic substances, you can cover the entire table we are in front of. So the materials are not so cheap itself, but the amount of material you need to prepare your detector is very, very low. And yeah, that's basically it. That's the idea behind. Okay.
And you know, I can't let you off the hook because I get that question quite often from our clients. Again, like how low can we actually get? What's the potential of that technology when it comes to reducing the price?
That's a very good question, because this is a spectroscopic technology which is really capable of scaling. So you can really produce hundreds of thousands or millions of those chips with quite conventional technology. Production facilities, and then you have these sensors going down to maybe 2 or 3 digit dollar costs.
Okay, yeah, and that of course is appealing to a lot of applications that we deal about in a second. But let's finish up the list of advantages, and there's the fourth advantage missing, which is the speed. Now you mentioned that we can measure very, very fast. How can we do this? Why are we very fast, and why is that important?
So we have no moving elements, so you don't need any translation time to move any component. And first and second, we have these are PIN photodiodes, and they are extremely quick. So the readout can in principle be done in the nanosecond range. Of course, electronics is not capable of taking the same speed as our sensor can, but we can measure in the micro or millisecond range the entire spectrum.
Wow. So there we have it. Basically, four advantages. We have no dispersive element. We have a good spectral coverage. We are very quick, and we can achieve low costs. Now, all of these four are already very impressive on their own. But I think what's really remarkable is that they are combined. You get, with our technology, you get the combination of the benefit of the combination of all four of them. Now, this opens up completely new markets. This opens up applications that haven't been able to be addressed before. From your point of view as a CTO, like what kind of applications, what kind of markets are possible with that kind of technology?
So first, to my opinion, the biggest transition is to get out of the lab first into handheld devices. So you can carry your spectrometer with you. It's equipped with a battery, and you can measure wherever you are. You can take your measurements. And you can go even farther. You can implement this technology basically into a smartphone. So this technology with all your USPs you mentioned is able to get implemented into a smartphone. And then you can imagine about the applications which are possible. They are endless.
Okay. Well, of course, we have to say that it's not only a question of hardware, it's also a question of software, it's a question of algorithms, it's a question of, how do you do the chemometric modeling? And we touched upon all of these questions in other videos, so feel free to have a look. But there's one other thing that a lot of people ask me about, because especially those people who are very familiar with spectroscopy, and they look at their lab and they look at their spectrometers that they have, and they ask me, you guys have only 16 pixels. My lab spectrometer has at least 128 or 512 or even more than 1,000 pixels, meaning more than 1,000 wavelengths that I can cover. And you guys, with your technology, with Senorics technology, can only cover 16. How is that even able to compete with a conventional spectrometer? So what would be your response?
That's a very good point, basically. So when you have a look onto an NIR spectrum, you will see that the features are smeared out, they are broadened, and you can now use 1,000 pixels and 1,000 wavelengths in order to extract information on that. But then you will see that the information content is sitting on specific points, and they are not 1,000 points, they are more or less a few points, 10 points, 20 points, which you need to analyze in order to get the full information out of the spectra. So we can extend extend the amount of pixels, but we don't need to, because 16 is really enough to get information out of the spectra. And so far we do not encounter any application which you cannot address with 16 pixels, because usually we take much less. So 3, 4, 5 pixels are enough for certain applications.
Yeah, interesting. So I'm personally a big fan for always focusing on what's really necessary and leave out all the rest.
Exactly.
Yeah, and that's exactly what we do.
Yeah.
Okay, but just to clarify for our viewers, that would actually mean that we also at first have to identify the specific wavelengths that we need to address. So even us, we also need a full spectrum at first to really identify which wavelengths are needed, and then we can build corresponding chips and corresponding applications.
Yeah, this is one way. So we can use a standard spectrometer in order to learn where the music is playing, and then to customize a chip on that. But we can also produce a spectrometer-like sensor, which has equidistantly spaced pixels in spectral region, and then we can directly step into the application, which is maybe then not totally optimized, but it's still accessible.
And obviously, for this kind of stuff, we need specific chemometrics, we need specific modeling, specific statistical and mathematical methodologies, and this we will cover in one of the next videos. But before we conclude this video, let's come to another question that I get very often from our customers and our clients, and this is the question of lifetime. When a lot of people hear organic electronics, they immediately think of, ooh, I heard that organic electronics, they are not stable and they deteriorate very fast. So they are concerned that it actually will not be in good shape over a long period of time. What's your take on this?
So again, organic material, it's not living, so it cannot die. Short answer. So all the disadvantages the organic technology had in the past is solved basically, so we don't have problems with lifetime. It's stable.
Yeah, cool. That is a very good remark at the end. It is stable, and so are we. So thank you very much for watching. This was our video about the Senorics technology in general. And if you would like to learn more about material sensing, about Senorics technology or other topics, feel free to either contact us, go to our website, senorics.com, go to our social media channels such as YouTube, Facebook or LinkedIn, and especially sign up for our free Explore and Understand package that you will also find on our website. So yeah, thank you for watching one more time, and happy analyzing.